Alright, let's take a look at GCL3. This video covers worksheets 1 and 2 material. The topic that we're looking at right now is everything about symmetry. And this objective uses a phrase that might be new to you, which says, or the phrase that gets used is to carry a shape onto itself. Now, ultimately, to carry a shape onto itself is the idea of what symmetry means. So really, this is a tricky word for symmetry. But to carry onto itself might be something that looks like this, for instance, if I can draw it correctly. The letter T, for instance, if I draw a line of reflection down the center of it, this line of reflection would carry this half of the shape onto itself completely. There would be nothing left over. Same idea here. If I had a square and I began to rotate my square, after a 90-degree rotation, I would be carrying onto itself. So this phrase really is a code word for symmetry. What kinds of symmetries are there? There is what we call reflectional symmetry, or probably more commonly known as line symmetry. That's like this one here. This is reflectional or line. There's another type of symmetry called rotational symmetry, like this one here, where as we rotate the shape, it rotates onto itself. And then another one we call point symmetry. The way point symmetry works is that, if I can draw this correctly, that each point on the shape, let's say this point, has a matching point, same distance, but on the opposite side of the shape. So this guy's over there. Or I pick this point, it has a partner exactly on the opposite side over there. We'll look at all three of these briefly now. The first one we'll look at is line symmetry or reflectional symmetry. And so kind of what do we have for a definition here? So basically you have line symmetry if a figure can be mapped onto, there it is, onto itself, a reflection. Very simple idea that basically if there is a reflection such that it would map it onto itself, this is known as reflectional or line symmetry. And again, that comes in lots of different forms. The letter M, for instance, has line symmetry because there's a reflection that maps it onto itself. Let's take a look at a few examples of this. Here are some good ones here. I think the letter A, we've worked with it long enough to know it as one line. Now this letter Z, lots of students think that there's like a diagonal one here, but I'm going to use a piece of patty paper. And what it is, what patty paper is a thin little piece of paper. And I'm going to quickly sketch this guy as best as I can quickly. And I'm going to attempt to reflect it onto itself. Now the way you would do that is to fold the paper. And I can't fold it so that in any way that I try, it's impossible for me to fold this so that I place it onto itself. So I just, in terms of being able to do this, I'm going to try and fold it, but I couldn't. There's no lines of symmetry there. Our butterfly, if it's done perfectly, would be one. This triangle sure doesn't look like it's doable, but let's try it out. Again, I'm going to use my patty paper to trace over it, and then I'm going to attempt to fold it onto itself. Now, I don't know how well you can see that, but it isn't going to happen. I guess hopefully you can see that. So there are no lines there. Here we have 1, 2, 3, 4, 5, 6 lines. Here there are 4 in our square. This parallelogram is a good one too to test out with the old patty paper. It seems like it should work, but I think if we fold it sideways, we see that it doesn't. And a lot of students think to do it diagonally, so I'm going to try and do it diagonally. But I think you can see that it doesn't work that way either, so none there. This is also 0. This may look good, but it's more rotational than it is line. One more thing to talk about with line symmetry. These fun little shading ones. I'm not going to do all of them, but I'll do a couple quickly. This one says shade the blocks so you get exactly one line of symmetry. So my first idea would be to shade this. Now this would provide me two though. I could do vertical or I could do horizontal. So I better eliminate the horizontal one. And so this is one answer. There's my line of symmetry there. Let's do a different one. Let's do this one where it wants 4 lines of symmetry. Well, I could do this, this, and this. I would create one here, one here, one here, and one here, and so on. Alright, let's take a look at rotational symmetry. Rotational symmetry has 2 things that we want to keep track of. One is the angle of rotation. This is the smallest angle in which the shape is carried onto itself. So once again, this idea of onto itself. So if you can rotate our square 90 degrees and it lands on itself, 90 degrees is the angle of rotation. Now the order of rotation is basically the number of positions in which it carries onto itself. So if a shape like a rectangle, as I rotate this 180 degrees, it would carry onto itself once there, and then as I did it again, it would come all the way back a second time. It would have an order of 2. Now if the shape had no rotational symmetry, let's say the letter M, and as you rotate that, it went all the way around and never rotated onto itself, it would have a rotational value of 1. Now that's weird, to have 1 mean no rotational value. But really what that means is you went all the way around and it didn't see itself. Let's take a look at some examples here. This one's a little bit more new to you. Let's look at this one. You can kind of see the swirl here, where if this guy rotated once, it would land there. If it rotated again, it would land there a second time. And then the third time would land here. So it has an order of 3. And an easy way to know the value is 360 divided by 3 is 120. Here, I'm going to use a piece of patty paper to help me here, just because it's easy to copy this down. I'm going to quickly jot my S down. And I'm going to keep track of kind of how many times I'm rotating to get onto itself. So here we go. So at 90 degrees, I am here. At 180 degrees, I am onto itself. So once. And then at 270, nothing. And then back at 360, I am there. So once, and then a second time when it came back, order of 2, 360 divided by 2 is 180. Let me do just one more, again, to give you the same idea. I'm going to again copy it down with some patty paper. It's very helpful to help me. I'm going to watch this corner here. I rotate it 90. I rotated it to 180, and I carried onto itself once, and then 270, and then 360. I came back to it a second time. Order of 2, angle of 180 degrees. Let's do a couple quick shading ones here. Maybe just two quickly here. To get an angle of 180, an order of 2, we'd probably shade straight across. To get an angle of 90 and an order of 4, I would need to be able to rotate it, once, twice, 3 times, 4 times. Finally, let me just talk about point symmetry. We're not going to do much with it, but point symmetry exists in a figure built around a point such that every point in the figure has a matching point on the same distance in the opposite direction. And so it will, because of that, it'll always have an order, at least an interval order of 2, or a multiple of 2, because that 180 will always be a part of the point symmetry because of that opposite side and opposite direction. So again, what it means is that if I can pick a point and go through a center point to its opposite distance, opposite side, and it lands on the shape every time, it has point symmetry.